This is the brief on the necessity and derivation of Christoffel symbols. So even in totally flat space, if you use a coordinate system that's curved or rotating like, say, spherical coordinates, things get tricky. Suddenly, describing something as basic as a vector keeping a constant direction, a process we call parallel transport, gets, well, complicated. And that's exactly where Christoffel symbols are essential. First, let's talk about why we even need them. Imagine a vector just sitting there, pointing straight in a simple Cartesian grid. Easy, right? But if you describe that same vector in a curved system, its components start changing all over the place, even though the vector itself isn't moving. Christoffel symbols are the correction factor. They tell us precisely how much the components have to change just to make sure the vector is truly maintaining its direction. Okay, second, how does this work mathematically? Well, these non-zero symbols are what make sure the covariant derivative is zero. You can think of the covariant derivative as a smarter way to measure change, one that already accounts for the curved coordinate system. So setting it to zero correctly represents the physics of a truly constant vector. And finally, the source material gets practical. The task is to actually compute the components of the metric tensor and the Christoffel symbols, specifically in spherical coordinates. You do this by starting with the basis vectors for that system, the ones that point in the r, theta, and phi directions. Mastering how to calculate and use these symbols is really how we ensure physical laws hold true no matter which coordinate system we happen to choose.